My name is Jim Nitterauer. I'm a senior security specialist with AppRiver. AppRiver was just recently purchased by Zix Corporation, so I'm not sure whoever was still working all that out. That just happened a few weeks ago. So this talk is entitled Decrypting the Mess that is SSL TLS Negotiation, Preparing for the 2020 Apocalypse. A disclaimer, this isn't going to be very technical. It's going to be a good overview of SSL TLS and what you need to do to make sure things don't go wrong when this happens, but I always have to do a fancy title to get the talk. All right, so disclaimer, this information you're going to hear today is just for your own security and privacy posture. It shouldn't be used for unethical purposes. You could do that if you want to. Concepts presented are not my own research. They're just information that I've gathered from other sources. The information presented is gathered from public and private sources, and I'm giving credit where that's due, and the views expressed in this talk are mine and not necessarily that of my employer. I've spoken in a bunch of different places. I'm on staff besides Las Vegas, spoken at DEF CON, Circle City Con, ViveryCon. Just tend to get involved in these conferences, so I have a little bit of experience in this stuff. I saw an invite to come to CypherCon from a friend of mine named Schwartzberg, and I was trying to think of something to talk about because normally I talk about DNS, so this is for Will. This is the only mention of DNS in the whole talk, so you'll have to watch the talk to know what that is. I saw this come across my desk in my news that I was reading where Chrome, Firefox, IE, which is now gone, so you forget about IE. It's now Edge, which will be Chromium in the next Windows major update. And Safari are going to disable TLS 1.0 and TLS 1.1 support in 2020. This specifically is going to happen by the end of March 2020. It's already happened in some versions, but this seems like a pretty benign headline, right? Well, think about the implications of this from an end user perspective and from a server perspective. And that's kind of what we're going to look at, so that if you either are IT, desktop management, your internal management, you know how to prepare for this, or if you're running servers, websites, APIs, mail servers, you can start to look at your TLS SSL setup and make sure that you're going to be compliant so that people don't call you complaining, hey, I can't get to your website, or hey, why is your website not working in my browser? Why is your email server not working? These are the kind of things that kind of bite you in the butt if you don't pay attention to them. So we want to go over some things about how to avoid those things from happening. So today we're going to have a quick overview. We're going to look at the different versions of SSL and TLS, look at the differences in the history. We're going to talk about the SSL negotiation process. But going forward, the terminology should be TLS because SSL does not exist anymore. It's been deprecated completely and shouldn't be used anywhere. We're going to look at the differences between TLS 1.2 and TLS 1.3, which was just ratified last year. We're going to look at why SSL and TLS version support matters. We're going to look at some of the vulnerabilities and the types of attacks that can be carried out against TLS and SSL. We're not going to go into much detail. I'm just going to give you a quick overview of some of them and the basic mechanisms of how they work. We're going to look at some strategies for monitoring TLS negotiation at the edge of your network. This is important. You have to know what your clients are trying to connect to, how they're trying to connect, and how that conversation happens. We're going to look at some example data from that. I'm going to show you data that we use in production. It's nothing proprietary. I'll just show you how we prepare for this in our environment for one of our services. And we're going to look at some ways we can take that monitoring and use it to implement some protection on our network to keep some of these attacks from happening. And then I'll give you some resources at the end to help you on your tasks for getting TLS and SSL ready to go. So what is TLS SSL? Basically, the overall goal of TLS is to protect the privacy and integrity of data flowing over connection between two endpoints. Typically, the first thing that comes to mind is what? Web browser, right? Web browser, HTTPS, that's a TLS SSL connection. But it also works IMAP, SMTP, it works in every API, every application on your phone should be using SSL or TLS between the two endpoints. So basically it's a way to achieve that the client knows that the endpoint server is validated, it's who they think they are, and that the data in between is encrypted in some agreed upon encryption mechanism. So how does that happen? It's basically a two-step process. The first step is using public key or asymmetric cryptography. So you have to have a public key that's managed by a trusted source, a third-party trusted source. Verisign, Let's Encrypt is pretty common now, right? So Let's Encrypt certificate. you validate who you are as a server, as a recipient of the connection, by providing your public key out to the world. My client then looks at that public key, sends a request to you, you decrypt that encrypted connection with your private key because it matches, and now we know that the two are validated. And then once that connection, we'll go into more detail how this happens, once that connection is then established, the authentication, we switch to a much faster symmetric cryptography. Think of like an IPsec tunnel and a VPN tunnel. That uses symmetric cryptography where a key is agreed upon at the time using the cipher suite and the mechanism or the method that they're, version of TLS that they're using, and that key is used for every conversation. They both know the key, they both use the same key, so there's no need for continuous asymmetric cryptography. So some of the things we have to look out for in SSL and TLS is that it's validated through a public key cryptography. Now you can do this internally with your own self-signed keys, but that throws a browser error unless you generate a certification key and import that into your browser. So there's ways you can get around that internally, but typically we're talking about public connections to public-facing servers, not internal connections. The PKI always has a certificate revocation path. If it doesn't, you won't get an A+ on your grading for your servers. Perfect forward secrecy. Anybody have heard of that term before? All right, so what this means is that every time there is an agreed upon symmetric key used to encrypt the second part of a connection, that key has a nonce or some sort of padding that's agreed upon by both sides, and it's used one time to generate that key. So that's important because what if somebody compromises a server and gets your private key? If they've been sniffing your traffic over time, even if it's encrypted, if they have your private key, they can decrypt all of that traffic, right? Because then they know what the agreed upon a symmetric key was. But if you change how that symmetric key is generated for every connection, they cannot decrypt anything but that one connection when they get the private key. Okay, so it's a way to prevent that from happening. And it should always be in play. It's not always in play, and it's not supported in the older versions of SSL. The other thing we have to look at are what client-server applications are we talking about. The most common one, obviously, is HTTPS. IMAP, that's what everybody pretty much uses on your phones. You have Google Mail, that's an IMAP, but it's done through secure IMAP. I think that Exchange is done through HTTPS. You should be using SMTPS. Has anybody ever been to DEF CON and seen the wall of sheep or wall of shame, where people are using insecure POP and SMTP to send email back and forth? Their passwords and their usernames show up in clear text on the wire, right? So you can wire chart them, throw them up on the screen and see what they are. That's why you want to be using the encrypted versions of these protocols. So brief history. SSL was introduced by Netscape in 1994. It was never released in version 1 because there were some serious vulnerabilities in it. Version 2 was released in 1995. So keep in mind the timeline here. 1994, right? 25 years ago? Is that right? Am I doing my math right? Yes. Yeah, 25 years ago. So SSL version 2 in 1995 was the first usable version of SSL. It wasn't used for a whole lot at the time. Version 3 was released 1 year later. And we're still seeing SSL 3.0 out in the wild after 23 years. It fixed several design security flaws. TLS 1.0 was released in 1999, so not for 3 years later. It's an upgrade to SSL version 3, but they introduced the vulnerability into that protocol, and that vulnerability is the SSL fallback mechanism. Really nobody thought anything about it, but now it's one of the biggest ways that people can do DDoS attacks against services that still support downgrading of TLS connections. And I'll explain more about this in a few minutes. The next version of TLS came out in April 2006, so we're looking at 7 years later. It protected against cipher block chaining attacks. In 2008, so 2 years later, TLS version 1.2 came out, August 2008. I put the RFCs in there in case you want to go back later and look at those. And it added cipher suite specific pseudo-random functions. And this is where it came into the ability to create the perfect forward secrecy so that you could not decrypt previous conversations if you got the private key. It also removed a couple of the less secure cipher suites. SSL version 2.0 was deprecated in 2011, and it's been recommended for complete abandonment. It has been removed from pretty much every browser that's out there. If you try to connect by SSL 2.0, it's just not going to work. If you have services that are using it, it won't work at all. TLS version 1.3 was released in August of last year with the RFC. It's a 10-year revision process from TLS 1.2. It removes several of the less secure ciphers. So SHA-1, MD5, RC4, DES, and triple DES are no longer going to be usable in TLS 1.3. And it also does something called the server name identifier encryption. So, how many of you have looked at encrypting and decrypting SSL connections on your network, where you can actually look at where they're going? So one of the things that you see if you're using TLS 1.2 or above is a server name indicator, which is basically an unencrypted packet that tells you the domain name that you're going to and coming from within the encrypted TLS, or within that encrypted string. Well, TLS version 1.3 is going to encrypt that. So any security that you're doing on any kind of TLS connections with 1.3 you won't be able to do. You won't be able to do man-in-the-middle attacks very easily with this new version. So it's going to change how security is done for TLS connections. There's a couple of resources here. If you want to look at a long history of TLS and SSL and all of the vulnerabilities and how it's done over a timeline, that feisty duck link is a pretty good place to start. So let's look at basically how the TLS SSL connection process works. And this is going to apply to both SSL, TLS 1.1, 1.2, 1.3, it all works the same way. So this is the OSI model, basically the TCP version of it, a network layer version of it. So all of the connectivity happens at layer 4 and below for the TCP connection, but within that, then there's the application layer, which is, can be HTTP, it can be SMTP, IMAP, doesn't matter. But everything else is the same. So the first stage in this is the SSL handshake. This is the part that relies on symmetric key cryptography. The second part is the SSL cipher exchange and the actual data transfer, and that's all done through asymmetric cryptography. So this is just a visual on how all of this takes place. So part one, what happens basically to every SSL TLS connection, it determines a cipher suite to be used, it determines a protocol version to be used, and it requires asymmetric cryptography. Keep in mind that the public key is validated by the certificate, and the private key is known only to the server. Typically, this is only a one-way authentication, so if your browser is making a connection to somewhere that's secure, your browser gets the certificate publicly, validates to the server. Now, there are times where certain types of connections, has anybody ever been to one where they require that you have a client certificate? Okay, so this is the same as if you go to like DEF CON or a bigger conference, you'll download a certificate to get on the Wi-Fi network. You're basically validating that your client is valid to the server, right? Not the other way around. That happens sometimes in TLS SSL connections, particularly when you're doing end-to-end transfers of funds, maybe two banks transferring data back and forth. They'll require that both ends of that connection do an authentication. So they call that two-way authentication. But most of the time, it's only one-way authentication, and you're never prompted for a certificate in your web browser. Keep in mind that TLS version 1.2 and less requires 3 round trips to the server, 4 if you're doing the client authentication as well. So this gives you a little overview of how that works. First thing happens is you log in, you type in HTTPS, whatever you're going to, and it goes, hey, I'm a client out here. I want to send some data to you, but I want to do it securely. And here are the cipher suites that I support, and here's the protocols I support. The server goes, great. Send back, here's the server, here's the protocols I support, here's the cipher suites I support. Then they both agree on hopefully the strongest cipher suite and strongest level of support. And then what will happen is they agree that they can talk to each other because the certificate matches, it decrypts. Now we go to the asymmetric part, what's called a pre-master key. I'm sorry, the symmetric part. The pre-master key is generated using a public key. And then after that, the keys are exchanged, so they both know the same key that they're going to use for exchanging the data at the data transfer layer. So that's basically a handshake process, and the data transfer happens at the very end of that, the last step. So So after agreeing on a session key, or we'll hear this, the master session key, there's different terminology, so it gets a little confusing. All the communication between the endpoints occurs via the use of that negotiated key for encrypting and decrypting every packet that goes across that connection. So if you're in an HTTP environment, you've got keep alive, so the connection stays open for a long period of time. Typically in an email connection, you've got pipelining of messages from one mail server to the other, so you're not renegotiating that connection for every message that's getting sent. And that information stays current until the connection's dropped. Once that connection's dropped and you renegotiate a connection, you have to go through the whole process again to restart and gather the certificate and agree upon the master session key. This is done to protect so that if somebody gets your private key, they cannot decrypt every session that you sent across to the server in the client. This process is mostly seen in web traffic, but again, it applies to every type of encrypted traffic. It's the same process. Just different ports, just different protocols underlying the application layer. All right. So TLS 1.3 is a little bit different. The same basic information has to be exchanged to establish that connection, but the process for exchanging the data varies. First thing that we have to remember is the server name identifier. No worries. The server name identifier will be encrypted within the packet. So if you're doing firewall, IDS in the middle trying to decrypt on the fly, or you're trying to decrypt a load balancer, you're not going to be able to see what the information is in the server name identifier. The only thing that can see that is the server endpoint once it's decrypted on the machine that has the private key. The process that does this results in only one single round trip between the server and the client. Whereas remember, SSL, all the SSL versions of TLS 1.2 and below required at least 2, if not 3 round trips to the server to make that connection before it could transfer data. So TLS 1.3 also has something built in called zero round trip time resumption. This is the way that the client can reuse that agreed upon key with the server. The server stores the secret from previous sessions and can reuse it for that client for some given period of time. And that's typically configurable on whatever platform you're doing. Now this, you would think that's kind of stupid, right? Somebody could then steal or look at that key somehow and use it to decrypt, or worse, they could encrypt traffic and send it as you, right? They could spoof who they are and send it to the server. The server has ways around that when it's using TLS 1.3. There are some features that are built in, and I'm not fully familiar with how it works exactly, but when I did look at the fallback mechanisms, it is very secure. It's not that you can't break it. The lack of full forward secrecy is not something that it allows you to do. And TLS has mechanisms built in to deal with both. So this is a diagram, it comes from Cloudflare, but it's a diagram of how the two different handshake mechanisms work. So you can see that, and this doesn't show on the screen, unfortunately, but if you look at the left side, your left side, that's TLS 1.2 and less. There's 3 round trips, well, 1, 2, 3 round trips to the server to get that to work. In TLS 1.3, there's only 2 round trips, and the data is encrypted at that point. So the speed of the connection is much faster, the response time is much better. One thing that you do have to realize is TLS 1.3 requires HTTP 2 to be enabled on whatever web server you're using. If you're using web services, not every web server that comes out as a main release supports HTTP 2. You have to do some extra work to make that happen. So that's something to keep in mind. If you're trying to implement TLS 1.3, it's not going to happen in Windows yet. Microsoft uses S-Channel as their core libraries for doing encryption and decryption. Then think of S-Channel as OpenSSL for Windows, same idea. So S-Channel does not have support for TLS 1.3 built in at this point in time. They probably will not put it into Windows 2008 of any sort. So if you're using Windows 2008, you're screwed, okay? You're going to have to upgrade at least to 2016, but I would say if you're going to do that step, go to 2019. It's far better. And then they will support it for that, but it's not in production yet. So here's an overview of the things that have changed in TLS 1.3. Some of the features that have been removed include the static RSA handshake, that's gone. Cipher blockchaining, MAC then encryption has been removed. Okay, this has been shown to be spoofable, so they've removed the ability to set this as a way to do the encryption. So now the MAC is encrypted inside of the package that's sent, so you can't see what that is, and it can't be spoofed. SHA-1, MD5, RC4, triple DES and DES have been removed. Compression has been removed. It's not needed because it's cut out a whole entire round trip. And renegotiation is not possible. So once the connection is good, the connection's good. If it has to renegotiate, remember, it remembers the secrets, and it doesn't through a whole different mechanism. The features that have been added is full handshake signature, so that's that first trip. Everything in that first trip gets all of the information it needs to be able to establish the protocol and the cipher suite that's being used. It's also added some things for elliptic curve. Anytime you see EC in one of the cipher suites, that stands for elliptic curve cryptography. Elliptic curve cryptography is something that gives you, how can I explain it? Gives you a higher bit count encryption level with less bits processed by the processor, if that makes any sense. So you can get something like 2048-bit encryption with maybe an 860-bit key using elliptic curve cryptography. Doesn't seem like it's a big deal, but if you're doing hundreds of thousands, millions of transactions, it makes a big deal from a processor perspective. And there's several curve variations that have been added to TLS 1.3. So why is this important? Why do we care? We want our stuff to work. We just want it to work, right? So Chrome removed SSL version 3.0 in 2015. It's gone. You can't use it. You can't use it with Chrome. You can't turn it on. You can't force it to do anything. This effectively eliminates all SSL versions that are commonly in use. So if you're seeing SSL version 3.0 requests on your network, they're probably crappy old machines somewhere, old browsers, or malicious traffic. Okay? The longer it goes, the more it's likely it's malicious traffic. And I'll tell you why in just a second. The deprecated versions of TLS 1.0 and 1.1 are supported through version 72, which is what we have out, which is pretty much what's current now, but that's going to change because it was just a release of some 0-day in Chrome, so that number's going to change. Version 81 and above for Chrome will not support any TLS versions but 1.2 and 1.3. Okay, and that's coming out sooner than the March 2020 date. Akamai Cloud Services, so Akamai is a content delivery network. They just continue to support TLS 1.0, 1.1 on January 7, 2019. So they're ahead of the curve. All right, everything that they put out there, anything that, let's say, Netflix uses them to distribute their content, that's only going to be available via TLS 1.1, 1.2, or 1.3. PCI compliance deprecated TLS 1.1 in their data security standard on June 30th, 2018. TLS 1.1 is still allowed, but if you do compliance tests on your network, there's only certain cipher suites that are allowed to be enabled, and I'll show you how you can check for this. But most every merchant has switched to TLS 1.2 completely. Cloudflare has disabled TLS 1.1 and 1.0 in June 2018. So they're effectively at the 1.2 level. So a lot of the provider level services have already changed. Microsoft Office 365 only supports TLS 1.2 starting October 31st, 2018. There is no option in Windows, we already talked about that, to go to support for 1.3. Google, Microsoft, and Apple, and Mozilla, who does Firefox, have agreed to end TLS 1.0 and 1.1 support in March 2020. So right now, they currently say less than 2% of all traffic is TLS 1.0 and 1.2. That's not what we see on our network. I think they're lying. There's still a lot more machines and devices and things out there that are using these old versions and old libraries. And we'll talk about the problems of how to get around getting those updated, but some of them just will never be updated. TLS 1.2 or better is required for HTTP 2.0 to be enabled on your network, and I believe it's a strict requirement for TLS 1.3. So, and it's only going to offer a limited number of cipher suites. So SSL Labs estimates that about 94% of all existing sites support TLS 1.2. I think it's a lie. From our traffic that we've seen where we have customers that are proxying through a web filtering service that we run, we see a large number of people still trying to connect to sites using 1.0 as their standard connection. And we haven't turned that off yet because we don't want customers flooding us with calls. So bigger issue is going to be other services like SMTP, IMAP, and those sorts of things. So the thing that people are not thinking about in any great detail here are what are the compliance implications of not having the right TLS versions. So you're a large bank and you are required to be compliant with Sarbanes-Oxley. Sarbanes-Oxley says, well, we don't allow you to do anything to TLS 1.2, and we want that across the board. Oh, was that just your website? No, that applies to your email. So if you're exchanging email with anybody out there in the world, we want you to negotiate a connection only sent by SMTPS and only with TLS 1.2 or better. Well, how many people's mail servers support TLS 1.2 or better? Right, everybody's mail server that I know of is set to try to negotiate TLS and then if it doesn't work, try some other version, and then finally gives up and says, screw it, and I'll just send it in clear. Well, that's not compliant, and if somebody tests you for compliance, you're going to fail. How do you fix that when that's outside of your control? Do you not send messages to people who have email addresses on services that don't support the latest versions of TLS? This is a dilemma that has to be looked at and has to be fixed. Because what's going to happen is you're going to put the companies that are in these positions that have to be compliant over a barrel because the customers don't care. They just want the email, right? You can't go, oh, you have to be my customer. You have to be on this mail service. These are our approved mail services. Can you imagine the havoc that that's going to create? It's kind of a big deal. APIs for TLS versions also have to be checked, right? How many providers will be doing content delivery networks for your phone apps? Suddenly these, not your most popular phone apps, but smaller providers don't have the ability or don't have the knowledge, or they haven't bothered to build an infrastructure that supports these latest versions of TLS, and suddenly their apps don't work on your phone because the content delivery network won't send the data over the network. So there's a lot of dilemma here that's going to be happening. One of the things you're going to hear about, and I lied to Will, this is the second mention of DNS in the talk. You're going to see a lot of information about DNS over TLS and encrypted DNS, which would be a UDP packet sent over basically what's essentially a VPN tunnel between a DNS server, client, and server. DNS over HTTPS is slow as crap. I don't care what anybody says. DNS has to be light and fast, right? So the only ones that have sort of gotten it right with the encrypted DNS are Cloudflare. They have where you can set up your DNS so that the traffic is sent in an encrypted tunnel between your DNS requester and your DNS server. The only thing that's good for is to make sure that nobody's spoofing your DNS or reading the DNS packets that are going out. If you want to learn about DNS privacy, there's a whole lot of things that people can find out from your DNS that you're probably not aware of. You might want to look into the privacy of DNS. The other issue that's going to be a big deal are these IoT devices, right? A lot of them are built on Linux subsystems. They use the open SSL libraries to do their stuff. How many of them are updated on a regular basis, right? So what's going to happen to all of those devices that are out there in the world that are trying to negotiate back to their APIs at their companies that are providing the support for them, and suddenly the providers that are doing the cloud services or even the internet providers won't even pass traffic that's TLS 1.1 or SSL 3 or TLS 1. All of those devices are essentially going to be dead. They won't be able to function, right? Who's going to update them? Who's going to take care of those problems? And these are the kinds of problems that people aren't thinking about, they're not looking at, they're not considering the implications of these changes in the standards. So we're going to look at a few of these vulnerabilities here. I'm not going to explain what they are because I'm not an expert on these vulnerabilities, but these are some of the attacks that were out there going back historically. One of the big ones, anybody remember SSL script? Marlin Spike put that out. You used to be able to spoof people. You'd run I could sit here and run a Kali Linux box and pretend to be the Wi-Fi and get you to join up. You can sign into Facebook and I redirect your HTTPS to HTTP and be the man in the middle with all your traffic. It doesn't work anymore typically on most sites because most sites now use HSTS, which is HTTPS, HTTP, yeah, strict transport, yes. So now if you try to go to Facebook and they look at the headers, first it requires that it's HTTPS, and second, they're in a list of servers that are, or a list of domains that are allowed within the browser, and there's a signature that goes with those, so that they're looked up and they cannot be spoofed by a man-in-the-middle attack. So that's something that's gotten rid of those sorts of things. All of these different vulnerabilities, though, have had implications in the changes, and if you go and match these up with a timeline, we don't have time today to go into all of that. But if you look at the timeline of when these vulnerabilities came out, some of them are more critical, more severe than others. They led to direct changes in the TLS and SSL protocol versions. Some of the big ones that you probably remember are Heartbleed, right? So that was a vulnerability of an SSL library where somebody could get into a machine or send packets to a machine that would buffer overflow the memory and dump information about the private key into that packet back to them, and then once the private key is kind of game over, right? They could get in your machine and do all kinds of nasty stuff. Poodle was a little bit of a different attack. That was a downgrade attack. It was a vulnerability in SSL 3.0. So this is the main reason that you'll see a lot of traffic trying to negotiate a connection at one level. The server will send back that I support it, then the client will go, I changed my mind, I'm going to go at a different level. The server will go, yeah, okay, I accept that. And they'll keep negotiating until they get to the lowest possible level. And what's happening there is people are trying to use that downgrade capability to get back to the lower levels to exploit some of these vulnerabilities, right? So by fixing your TLS versions and limiting what your machines or your endpoints will accept, you eliminate all of those vulnerabilities from your network, right? By not addressing this, you leave those vulnerabilities out there, and some of them are pretty severe and very well documented on how to exploit them. But you can see that there's all of these different ones that have come up. And what I'll do is I'll put this talk out so you can get at it, and there's some links that will talk more about all the details on all of these. But basically, every one of these attacks is initiated. Typically, it's either a man-in-the-middle attack, where the attacker intercepts a connection at the handshake stage and then alters the handshake if they're trying to exfiltrate data from that connection. And then they're going to go and request something to force the client and server to renegotiate the connection until they can get it to a level where they can basically sniff the traffic for a period of time, and then in the background they can crack the keys that were used to encrypt that traffic and then later decrypt the traffic. And in some of these, the vulnerabilities are so severe that they can crack the key in real time. And once they do that, they can just read the traffic as it's coming across. So the things that you have to keep in mind here is that the server accepted and responded to these downgrade requests, right? So that's a bad thing. You as the owner of whatever service you're putting out there, you want to dictate what versions of TLS you're going to support. You don't want to allow your clients to request insecure versions. And the other problem is a lot of these servers are set up to use weak or deprecated ciphers. So the cipher suite is the mathematical algorithm that's used to generate the key that's used to encrypt the traffic at the second level, the asymmetric level. And if you use cipher suites that are too weak, they're more easily broken. So the trick is you have to keep up with the standards. I know this is not something many people do, but I'm going to show you some tools for how to deal with this. First, we're going to look at how we monitor for this on our network. If you look at a TCP packet that's coming in with the first handshake negotiation, the second and third bytes, I believe it is, in that packet will tell you what version, in this lower right corner there, it tells you the version numbers of TLS, the protocol version it's trying to negotiate from the client or from the server back to the client. So you can see that in the packet in both directions in a conversation in Wireshark. What we do is we look at that payload on, in our case, we use F5 load balancers to terminate the traffic. So you connect to our service, it terminates on the load balancer, and then we forward the traffic to somewhere on the background. Now, we do not decrypt the traffic on the load balancer. There's a difference. This is something that people don't think about too often. And this is a little aside that I didn't want to get off on, but I think it's important to know. many services terminate their traffic on load balancers, whether it's H8 proxy, F5 load balancers, whatever. A virtual server, a virtual interface that's on the front end, internet facing. And on the back side, then those connect to an array of servers, nodes through a pool of servers on the back side. Well, think about this. Would you rather have end-to-end encryption where the data is encrypted all the way through the F5 load balancer to the back-end server? Or do you want the F5 load balancer to be decrypting the traffic and have that traffic open on a connection between the F5 load balancer and the back-end server? This is an important question. It's not one that many people look at. It's not many that compliance standards look at, but it's a big deal, okay? So this means that if somebody compromises one of those back-end servers anywhere on that network, right? Because typically that network was shared among a variety of different servers. They can sniff the traffic on that connection between the back end of the load balancer and the front end, public-facing side of whatever web server there is. And that traffic's all encrypted, right? Username, passwords, anything, credit card data, it's all there, right? So if you're setting up your network, you definitely want end-to-end encryption if you can do it. I know it's cool to be able to do all of your certificates and everything else on a load balancer. It's a pain in the butt to have to manage more servers, but the security implications of doing SSL offloading on a load balancer are pretty severe if you don't know what you're doing. Okay? So that's my spiel on that. This is part of an I rule. This isn't the exact one we're using, but F5 load balancers use TCL, which is tool control language, to basically allow you to manipulate traffic on an interface before and after it processes on that interface. So all we do here, and it's hard to see, but if you get the slides and download it, all we're doing is we're collecting bits out of the TCP connection. We're looking at the second and third bit. We're matching it to a number. We're saying if that number is less than this number, which it means it's TLS 3 or 1.0 or less, we drop the traffic. Right? We don't want it. Just drop it in our network. Who cares? But we do log it. So what we did is I set up a, we have a Graylog cluster. How many have heard of Graylog? Okay, so you know, who knows what Splunk is? All right, so everybody knows what Splunk is. Everybody knows what log aggregation is. Send your logs from many sites to one. It's all integrated. You have an interface where you can actually search, do dashboards, that sort of thing. So Graylog is like Splunk. It's a log aggregation. Send your logs there, puts them in the Elasticsearch database. Then it has a specific format that it expects the data to come in. It expects the data to come in something called GELF, or log extended log format. So that this part here, the part that says where it sends, I don't know if you can see it, that long string, that's just a JSON packet that gets sent to the logging server. But this allows us to go and do some really cool things on the logging side. All of our connections are tracked using an I-roll, so we track the client connection and the server connection, right? So remember the handshake process. Client makes a connection, server makes a connection back. They should match. And I'll show you what happens when they don't. We set the decimal value to the lowest acceptable TLS version. In our case, we're dropping 3.0 and less. We will change that shortly. All the connections are logged to the Graylog server. We don't have any SSL termination on our load balancer, so this is all layer 4 transport layer traffic. We're not looking at the data at the application layer. So keep that in mind. You can tell at the transport layer what version of TLS is being used in your data, right? Because TCP is transport layer stuff. We drop the connections that are less than 1.0, and we still see a significant number of people trying to connect TLS 1.0, which is interesting. So this graph here, this is our dashboard that we use. Basically what it shows, something to have a bigger screen. The top part is all of the TLS SSL connections that we drop. So they're all the ones that are trying to connect to 3.0. We don't drop 1.0 yet, TLS 1.0. All of the connections on this side of the first big number there, the 191,000, that's the client connections. So the client connections should pretty much match the server connections back, right? So when those two numbers are not fairly equal, and they're not fairly equal, that's 11,000 difference. So what do you think that traffic is that's the 11,000 difference? They're all machines trying to do downgrade attacks on the end services, right? So they may send thousands of packets. Right now, we're taking them, but when we turn off 1.0, those numbers will come back to much more equal if we exclude 1.0 and 3.0 as the SSL version. So it's an indication of what's happening on our network. We use it because we can actually tell what clients' IP addresses are sending what type of request to us. So we can go back and look at the IP, the source IP of the request. We can go to a client and say, oh, you know, you have devices on your network that are sending us SSL 3.0 connections. Oh, I didn't know that. Well, let's dig into that a little bit more, right? Sometimes they find that there's things on their network that they didn't even know existed. And this is only for a web proxy service, so this isn't everything that we do. We could apply this to email. We filter email for about 14 million email boxes, so we get a little bit of traffic on the email side. We host about 400,000 exchange boxes at the moment, and I don't know what our sister company Zix does. They have as much, and I don't have much insight into what they do at this point. We're just starting the merger. So this is just an example of how we can look at this data. We can manipulate this data, create different dashboards. We can alert when somebody's trying to do more than X number of connections. The other thing we could do at the load balancer level is we could go back and say, how can we make this better? We can go and we can actually look at the cipher suites. In the TCP connection, it tells you what cipher suites are trying to negotiate as well. There's other pieces of information in that packet that you could look at. We could rate limit the number of TCP connections, trying to make connections to our SSL, right, to prevent DDoS attacks. We could do key exchange validation on that to see what kinds of keys we're trying to validate on. We could apply this to other types of interfaces. So to get this working, basically you need a load balancer, something wherever your endpoint is. You could do this on a server as well, I suppose. You write and test the rule. I wouldn't do this in production. Apply it to the desired interface and configure remote logging. Now, the logging is going to be different on every type of platform, and there's other talks that I've given on how to configure remote logging for Windows and Linux. And there's a bunch of tools out there. So if you have a specific question, feel free to hit me up and I can point you in the right direction. We do have a Graylog cluster that we use. I think it's 4 nodes on the front end and a big Elasticsearch cluster on the back end. But really, the only tools you need to test to make sure this works are Wireshark or TCP dump on the load balancer. And maybe if you want to try to generate your own package, you can do some escaping and generate your own TCP package with SSL encryption to see if the rule works. Here's a whole ton of interesting links. I'm going to go over a couple more things, and then I think we're going to be pretty much about out of time. So these links will be in the slideshow. But one of the things I want to show you here is what you see when you go to ssltest.com. This is something put out by Qualys where you can actually go and test the quality of the SSL or TLS or HTTPS, whatever you want to call it, installed on your different platforms. I would recommend if you're a system admin, you do this. I don't have all the output here, but basically this shows you what are the websites that we host in an experimental environment. It's running TLS 1.3, it's running on Nginx, and I'll give you some parameters here. And a couple of the things that you want to look at, it does do the strict transport, and it also does, there's a record that you can put in your DNS that will improve your TLS scores. All providers now expect you to create a specific text record in your DNS for your domain, and that text record tells you which certificate authorities are allowed to generate certificates for your domain. Okay, this is important because somebody can generate a certificate for your domain without your permission if they intercept an email, get an email account for an admin at your domain, right? They can generate a certificate for some other domain or for your own domain and spoof traffic to a subdomain for your domain. If you're using a wildcard certificate, this DNS will help sort that out for you. This is a separate test that does compliance testing for websites. And this is the same website that had the TLS 1.3 applied to it. Now it passed PCI compliance 100%. There are 4 issues found for HIPAA compliance and 4 for NIST. The only issues that were found on this site were cipher suites that were enabled. That have to be disabled, and I just didn't have time to figure out how to disable them to get that to work. But if you go through this, it gives you a whole lot of detail on the things you need to address to make your SSL TLS connections be as good as they can be. So the other thing you want to look at, this is what we saw back to the SSL test site. These are the ciphers that were used, that are available. It tests every cipher against your platform. And if these come up in red, those ciphers need to be removed from your platform because they're insecure. But it tells you the bit strength, and it tells you which cipher it is and which ones they're in the order that they're preferred. So you always want to have it do the preferred ciphers first. Here's how I did this on running CentOS on a machine, a web server. I compiled Nginx with source code because the newest version was needed to do TLS 1.3 and HTTP2. I included the open SSL library 1.1.1. That version's needed for TLS 1.3 as well. I linked I had created new Diffie-Hellman key parameters for it of at least 4,096 bits, and then put that into the configuration, put an elliptic curve that it supports, and then there's the ciphers. I can give you more details, or I can send you the config for these, I don't care. If you want to do this on your own and set these up and test them, or need some help doing this with Nginx, you can do it with Apache as well. There was a bug that came out in Apache like a week ago that you probably, if you're running even the latest version, you probably need to patch to get up into the 1.39, I think is the one that's not broken. But the version that was broken, that's why I pulled it out of here, because I couldn't get it to work with 1.3. If you're in a shared hosting environment, somebody can upload a PHP script to get an account. A various person can get an account on your server, upload a PHP script, run that script through their website if you're doing it as a shared hoster, and they would have root access to your server. The vulnerability is that big in Apache, so you should look it up and check it out. So we're out of time. I think we're a couple minutes over. But if you have any questions, you can reach me there. My LinkedIn, that's my Twitter profile. But I'll be glad to help. I'm always available to help people make things better. So if you have any questions, feel free to ask, and I'll be around in a few minutes.